Okay, so first thing you want to do is go to our share dataset folder and download this file. So this contains the dataset for our example here. And then next you want to go ahead and open up Gradle. Okay, go to File, Open Data, User File, and just remember where you download it. I put it on the desktop. Now, when you download it, just keep an eye out what type of file it is. So our file is a CSV, so we have to go to CSV here, and just go ahead and go to Open. Now, it's going to always ask you that if you want to give it the data a time series or panel interpretation. No, this is a cross-sectional, right? We're not aggregating, we're not observing across time. Okay, so let's give you a little summary of what you inputted. Okay, just take a quick look and go ahead and close that. Now, we want to run a regression because we want our OLS estimators. So you go to Model, okay, and the method that we will be using, or the only one that we have covered in this class, is OLS, the ordinary least square. Go ahead and click that. Here we have. Now, you can choose any variables to be the dependent variable. So again, the dependent variable is the variable that we like to explain. Okay. Now, so in our model, we like to explain sales. Okay. You can set it as default. That's only if you're going to run this model over and over again. And so that makes it convenient. So if you click set as default, every time you open this dialog box up, it'll have sales here for you. Okay, so that's optional. We don't need that. Okay, and then now what do we want to use to explain? Well, we want to use population. So put that in the regressor. So again, regressor, explanatory variable, independent variable, right? Predictor variable. Right? These are all different names for the exact same thing. We're just talking about what is the x variable here. Once you have that, then you just simply click OK. All right, so now we've seen this before. Here's our coefficient, 60, that's our B0, 5, that's our B1. Okay, now we want the other, the SST, SSE, and SSR. So to get that, we go to Analysis. Analysis and go to ANOVA. That means it stands for Analysis of Variance. Click that, and here we go. Okay, so the top part, regression, that is your SSR. So our SSR is 14,200. Residual. Now notice how we said that different programs might use different names. This is very unfortunate. But residual is just our error. Okay, this is going to be our SSE. Okay, total, the obvious, that is our SST. Okay, so let's go ahead and write these numbers in our down in our handout. Okay, so from the regression output, what we have is we have SSR, right? That is the first one, and that is 14,200. SSE, okay, that is we call it sum of square errors, right? Gradle calls it sum of square residuals, right? And then that is 1,530. Okay, and then our SST equals 15,730. Okay, and then if you want to try, because remember, like, this is an important equation, right? SST equals SSE plus SSR, right? Go ahead and check, see if this is indeed true, right? And we can put that in the calculator. Okay, so 1530 plus 14,200, and that is indeed, right, 15,730. So that checks out. All right. So now that we have these three values, right, we can finally measure how well our model did. Okay, so we will use this index called the coefficient of determination. So it's simply R square, is pronounced R square, and it equals SSR divided by SST. Okay, and basically it equals explain the deviation over the total deviation. Okay, so for our case, for our example, 14,200 divided by 15,730. So that's going to give us 0.903. Now, how can we interpret this? Well, we can say, right, that with our model, or in another word, with population, right, we explained 90.3% of the total deviation. Right? And that is pretty good. Right? And as you can see, r squared, the higher the number, right, the better. Okay. All right. All right. Now, is there officially like an r squared that that will determine good versus not good? Not really. Right? These are just a measurement, right? And the higher the better. But we don't really say, oh, if it's past 60, then it's good. If it's under 60, it's bad. Right? So you be the judge of what is good or bad in that case. Now, okay, so let's deviate slightly. Here we have so there's a parameter that I'd like to introduce. It's called a population correlation coefficient. So it is represented by the Greek letter rho. So again, right, this is pronounced rho. It is a Greek letter. If it's a Greek letter, then it must be a population parameter. Okay, it represents the linear relationship between two variables. Now, it is very similar to beta 1. So beta 1, right? That is the slope parameter in our model, right? But it tells it's a different use than beta 1 because it represents the strength of the correlation. So I'm just doing some quick sketches. If x and y is positively correlated, then rho, right, and both rho and beta 1 or equal will be greater than 0, right? If x and y here, right, if they are negatively correlated, then both rho will be less than 0, and both beta 1 will also be less than 0, right? And if they have no linear correlation, then both beta 1 and rho, right, will both equal 0. However, beta 1, right, there's an interpretation of that. So for example, our beta 1 was 5, so that means for every student student or additional student in town, we expect the sale of pizza to increase by $5. Rho is scaled, right? And rho represents, rho represents the strength of the correlation, right? How, as x increases, how likely will y increase? Now, rho is always between 1 and -1, or I should say -1 and 1. Right? And it is equal if rho equals -1, then we say that is an absolute negative correlation. And if rho equals 1, positive 1, we say that is an absolute positive correlation. Okay, now how do we estimate rho? Okay, so we can use the coefficient of determination to estimate rho. And it's very simple and conveniently, right? This is why coefficient of determination is represented in r squared, because to estimate rho, we just simply use r. Okay, so r is the square root of the coefficient of determination, but we're going to take the sign that we got from B1 to use. Okay, so let's calculate the sample correlation coefficient for our model. So remember, our B1 was 5. More importantly, positive 5. So our sign of B1 is positive. Okay, and then now all we have to do is to estimate r, right, okay, and you can put r x y if you like, right? That just represent the sample correlation coefficient between x and y, and that is going to be positive square root of r squared, which is positive square root of, and what we got was 0.903, okay, and then calculate that out, then it's going to be positive 0.95. Right? 0.95. So that is a very strong positive correlation. Okay? And just one last note, right, whenever we're talking about correlation coefficient or just correlation, again, we're always talking about linear correlation. Okay.